Uh, okay. Well, that's new. Okay, so
Yeah.
the meeting is officially being recorded. So here we go. So last time, to summarize what we did, we proved associativity of natural numbers
Mhm.
and commutativity of natural numbers. And Rumi was nice enough to do that for us. Thank you, Mr. Rumi. And today, Avi is in charge of proving the cancellation law, 1.5.5.
Yes.
And as usual, we're going to work as a group through everything. But the floor is going to be Avi's to do as he likes. You know what I mean? And then we'll
Okay.
fill in. So okay,
So, you want me to go?
you're on. You just tell me what to do
Okay.
with the scrolling. Yes.
So, 1.5.5, which is cancellation law, it says right up there at the top, it says if x plus z equals y plus z, then x equals y. Because, yeah, cancellation. And so it says the proof for at the bottom, it says proof of 1.5.5, 1.5 for prime. It says denote x by, denote by x the set of all z for which 1.5.5 holds. And then, yeah, so we've got that. And as you talked about last time, you could have denoted it as a capital Z rather than capital X. But yeah, anyway.
Oh
Um,
yeah. I mean, it's weird to have Z's as part of an X set. You know what I
yes.
mean? It would make more sense to have a Z as part of a Z set, but it's no problem. Yeah, it's
And
fine.
so, yes, then it says we first show that 1 is an element of x, and that is from plus plus because if you go at the top at 1.5, x is part of it, and y, because we're assuming, then from plus plus it says that 1 would be, right?
Okay, so what you're saying is, let's take a look at plus plus before, right? So what you're saying is, okay, how do you get that from plus plus?
Because you have x, y, and 1 being in this set, and then at the bottom at for 1.5.5 it has x and y, and based on plus and plus plus doesn't it, therefore you can use 1 as well in if you've got x and y already in the set.
I don't see that. What I think is easier is the definition of x plus one
Mm-hmm.
is, yeah. Oh, okay. Oh no, no, now I understand. Okay, I'm
Yes.
looking at it backwards. So assuming this is true,
Yes.
then x must equal y.
Mm-hmm.
And I would say, right, I would say that follows directly from not plus plus, but just from plus because it
Oh yeah, yeah.
right? Because this is the least element that is bigger than
Yes,
x,
greater.
and
Yeah.
this is equal to least elements greater than
And so yeah.
x, and it's the least element that's greater than y. You know what I mean? So I,
Yeah.
I would actually go with just plus
Okay.
personally.
Mm-hmm.
Yeah,
Mm-hmm.
I mean, whatever. So
Yes.
yeah, so I
So
think this
yeah.
plus gives us a definition of what these things
Yes.
are, and the
Mm-hmm.
equal is key.
Yes.
So I think I said it. If you want to say it like really nicely, Avi, just for
Yeah.
clarity, so we have it
Mm-hmm.
on the call, I can restate it if you wish. It's up to
Yeah.
you.
Well, you yeah, sure you can if you want.
Okay. So this is the least number greater than x. Is that
Yes.
okay? By
Mhm.
one,
Of course.
and it's equal to this,
Mm-hmm.
two underlines.
Which is what we're assuming. Yes.
Yeah, which is okay. So
Mm-hmm.
this, yeah, just one
Mm-hmm.
second, This is equal to least number greater than x, right?
Yes.
And it is the, the least number greater than x. It's also
Mm-hmm.
the least number greater than y.
Yes.
Okay,
That makes sense.
right? By definition of it, and also
Yes.
by equality. So we have the least number greater than x is equal to least number greater than y.
Mm-hmm.
And
Yeah.
if x was not equal to y, then this would not be possible, right?
Mhm. And so then after that, it says by, so we're assuming that x, yeah, x plus 1 is equal, the least element greater than x is equal to the least element greater than y. And then by 1.2.1,
Oh, this
we
isn't,
have,
yeah,
which you
that's
can go
fine.
up to if you want, but by 1.2.1, yes, it says we have x is what, because that's trichotomy, right?
Yeah, the
1.1,
trichotomy is all three because
yes.
it's on the
Yeah.
other page.
So
Sure.
yeah, x is either less than y, x is equal to y, or y is less than x. And then so we take those one at a time. So the first inequality, which is x is less than y, is so that yes, this it gets a little bit complicated in my notes, but it says that if x is less than y and x plus 1 at the least element greater than x plus 1 is equal to y plus 1, then it says at the bottom that x is less than y and y is less than, which implies x is less than y and y is less than x plus 1.
So what you said is y is less than y plus 1, which by assumption is equal to x plus 1.
Oh, yes.
Yeah, right? So that's the key. That's where you get the second inequality from.
That makes more sense than, yes.
So so you have your case, you have case 1, case 2, and case, I can't do 3 underlines. I'll do a circle. So case 1, so case 1 is this, and then by assumption you have the second inequality. And so you're good. Okay.
And then so it's
and that's impossible.
Impossible because you'd be having something between x and the least element greater than x.
Yeah. So okay. So what you just said is case 1 is sayonara.
And similarly, the inequality y is less than x is impossible because it's just the variables are flipped in that situation.
Yeah, it's the same argument. Same argument. There's absolutely no difference in the argument. Yeah.
So we must have x is equal to y. So that's the first step, is that we've now done that.
Good.
And then it says in the second step, we assume that z is an x. That a variable, is an x. And show that z plus 1 is an x, which then by
induction,
induction it would be
exactly. So you're starting with 1, and now you're proving if z is an x, then z plus 1 is an x. So you're using the induction principle. I love it. Okay.
So it says if x plus z plus 1 is equal to y plus z plus 1. So I have that right here. I think I need to flip the page in my notes, but yes, and then there. So it says if if x plus z plus 1 is equal to y plus z plus 1, its assumption. Well, I got it. Okay, then by 1.5.3, which is 1.5.3, which is associativity, and 1.5.4, which is commutativity, we can rearrange that to x plus 1 plus z is equal to y plus 1 plus z, which makes
okay.
sense.
So you have associativity, which because you can play around, and you have commutativity. So rearranging all this nonsense, which is now allowable, gives us this. Equality, right? Which is beautiful.
Yes. Okay. And hence, by the assumption that z is an x, we get x plus 1 equals y plus 1. And that's saying because if we're assuming z is an x, then that means it applies for cancellation law.
Exactly. The cancellation law applies for z. We need to show it applies for z plus 1. Beautiful.
And so it then says, taking into account the first step of this proof, which was that we proved that y is equal to x, then you can now conclude that z plus 1 is an x. And I have a little thing where I said because if x plus 1 plus z equals y plus 1 plus z, and we know z is works with cancellation because we're assuming that, then you can take out then you can rearrange that to x plus y, x plus 1 plus z is equal to y plus 1 plus z, and then you can get rid of x and y, which we know are equal from the first step, and you're just left with 1 plus z is equal to 1 plus z, but you could also just get rid of 1 plus z because we know that y and x are equal. So it works with the cancellation.
Yeah,
and then you get that.
Yeah, if you get the cancellation law, you can just get rid of the z, right?
Yes.
And then you have x plus 1 equals y plus 1.
And so then you know that we can conclude that z plus 1 is an x.
Yeah, I think your argument is cancellation law, so just get rid of the z as the cancellation law, right? And I think that is, what's necessary, right?
Yes.
And since, x plus 1 equals y plus 1, we already know that, x and y are the same, right?
Which works out pretty nicely, so yes.
Awesome. Okay, any
and
questions?
Sorry, do you mind if I go to the bathroom quickly?
Take your time. Let's pause.
Okay.
Let's pause.
Okay, thank you.
Oh, no, no, that's different. Pause. Pause. Okay. Okay, so let's continue with 1.5.6.
Yes.
X and y are natural numbers such that x is less than y. There exists a unique natural number z such that x plus z is equal to y. Okay, so
Ah.
this, right? So first of all, we have to show there's a natural number, right? And then we have to show it's unique, right?
Mhm.
So, and I think we had a couple uniqueness proofs already at the
Saying that
beginning.
there's a single number that could be added to x that would equal y.
Yeah, a unique
Right.
number. Yeah, I'll let you say unique. But I think
Yeah.
we had a couple uniqueness arguments previous. So denote
Mhm.
x as a set of natural numbers, u such that x plus u is less than y. So this is now officially
Or
less
less
than
than
or
or
equal to
equal to.
y. Yeah, less than or equal to y. So this is a set, right? So you have an x and you have a y. This
Mhm.
is already given,
Yes.
right? X is less than y. These are given natural numbers from the assumption. And so take a look at the set of all xu such that x plus u is less than or equal to y. Now, this set is not empty because it contains the number one. That's already been done. Is
Mhm.
that okay? That was
Yes.
proof 1.5.2. Avi,
Yes.
I don't think you were around for that, but I mean,
That makes
I,
sense though,
I
because
think Ethan
yes.
actually,
Yeah.
we talked about that. To be
Because it'd
completely
just be
honest.
the next smallest number, the element greater, yeah, than x
Yeah,
because
you're
it.
gonna get a contradiction on the greater than it,
Yeah.
it's
Anyway,
not gonna
but
work.
yes.
Yeah, so let's just leave it there. But it
Yeah.
is from 1.5.2, and I believe an exact quote was Mr. Ethan actually discussed that. Actually,
Mhm.
is my recollection, but don't hold me to it. So this says not empty. Okay, so we have a non-empty set. Hooray! Right? So hooray.
Yes.
Moreover, it is bounded. Right? Why is it bounded? Right? So
That's
why is this set bounded? Anybody want to hit me with this?
because it is bounded by y
It's bounded
as
by y, and we're done. As soon as you put y in, it's going to be
yeah.
greater than. So clearly, it's a bounded set. Is that okay?
Mhm.
Is it, Rumi? Are you okay with that, Mr.
Yeah, it
Rumi?
makes sense. It makes
Okay,
sense.
so why? Yeah, like
So we got a non-empty then
why would yeah. Y plus x is not going to be less than or equal to y, right?
Mhm.
So that creates the bound dynamic, right?
Exactly.
So you're
Mhm.
good, right, Rumi?
Yeah, because x plus u, it says implies u is less than y, right? I mean,
Yeah,
Mhm.
I
if
mean,
we
yeah, I mean, I'm not even looking at any of this. I'm just sure. Yeah, essentially, I'm looking right here. You put a y in here,
Mhm.
that's
and
a
this
that's
is
not,
not
yeah.
true.
Uh-huh.
So, it would be bounded from above by y. The set would be bounded from above by y because obviously everything after y would also not be in the set. So y would be a bound for this set
Hmm.
because
Yeah,
every element after y would not be in it.
yeah,
So, and he gives this rationale. I
Yeah.
don't even get into that rationale.
Yeah.
I think the statement itself I think
Yes.
is self-evident in the way it was just expressed, right?
Mhm.
Um, so let z be the greatest number in x. Is that okay?
Yes.
Okay. And do we have a greatest element? Yes or no? I mean, do we have one? Yes or no? I mean, I
yeah,
guess,
because it's
Yeah.
bounded.
yeah,
Mhm.
that's axiom 3, right?
Yeah, that is, yeah.
Yeah. So
Every
this is not nonsense. This
non-empty,
is real, right?
non-empty.
So we
Yes.
do have a maximum element by axiom 3. Good, 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 good. Then by the trichotomy, x plus c
Mhm.
is less than y, or
Mhm.
x plus c is equal to y, or
Mhm.
or the opposite, right?
Yeah.
Whatever. No, because it's nice having the x plus c on the one side, less than, equal to, or greater. But well, it's the
Eh,
opposite. No problem. Is that okay? So we
yes.
have 1, 2, or 3. Let me change this a little bit. I'm gonna do that's 1.
Mhm.
This is 2, and 3 is going to be a circle, right? 3 is going to be a circle. Oh no, wait.
No, the
Sorry,
one up.
sorry,
You went
sorry,
down one
I
line.
went down. Sorry. Sorry, that's not what I needed. This guy, this 1, 2, and 3, right?
Yes.
All right. So the first inequality is excluded by 1.5.2. So what's 1.5.2? Let's go take a look at 1.5.2. If x is less than y, then x plus 1 is less than or equal to y, right? And I think this is the one that Ethan talked about specifically, right?
Yes.
So, right?
Yeah, because I was there for that. I remember.
Okay. So the first inequality, yeah, so,
Less
right?
than.
Okay.
Yes.
So what's going on? Why is the first inequality excluded? Because otherwise, we would have, yeah, the problem is if it's less than, then we would have the following also would be true by 1.5.2.
X plus z plus 1 would be, yeah.
Yeah, so that can't happen because if z is the greatest element,
Yes.
I can't have a z plus 1 as well in the set, right? That would contradict so that's a problem, right?
Yeah.
So this is officially eliminated, I believe,
Interesting.
right? Is that okay?
Yeah.
So we're okay with that. Rumi, you're good? Yes?
That makes sense. That makes perfect sense.
Okay. So yeah, you can't have z be the largest element in the set and have z plus 1 being in the same set. Right? But yeah, contradiction.
Yes.
Yeah. The last inequality is also excluded because z is in x, and thus x plus z must be less than or equal to y. That's the definition of the elements in x.
Yeah.
So you can't do the
Yeah.
I'm sorry, it's you can't have both, right? You can't have x plus z is less than or equal to y by definition of the set and have the exact opposite, right? Have
Yes.
y is less than. So this is also officially now eliminated. So what do we have? Well, we have x plus z is equal to y. Are we done? Not quite.
No.
So we have x plus z is equal to, sorry, that's not a good underline. So we have x plus z is equal to y, which is good, right? Which is good. Are we done was the next question.
No.
And no, why not?
Because you still have to isolate z to prove that because we're trying to prove that x the unique, that it's the only.
Yeah, so it's a uniqueness, right? So we showed that we have an element, but what's stated in the theorem or this result, excuse me, is not only that we have one, but we have a unique one.
Yeah.
So, one way to prove uniqueness is assume you have two. So suppose you have one that equals y and another that equals y, right? Is that okay? Assume you have two, right? And prove that those two are the same, which is actually very easy given what you just did, right? But if these two are equal, then you have
because now that we
this,
have
right? And because of what you just did, we have, z1 must be equal to z2. I think, what you proved was the right cancellation law. So actually, you have to rewrite it using commutativity first to have z1 plus x and equals z2 plus x. So use commutativity, and then you have your result, right? So I mean, yeah, being logical doesn't really make sense there. It's pretty obvious. I would say it's somewhat self-evident. I think if you didn't say commutativity, you get a thumbs up. If you say commutativity, it's thumbs up. It's the same thing. It's pretty clear.
Yes.
Mr. Rumi, are you okay? Yes or no?
Everything is okay so far. I feel confident that I know this.
Okay.
And I know how it works.
Okay. So here's where he talks about, like, I kind of like this little passage. So this is not part of the class, but let's just talk about this really quickly. This fact is known to every child in elementary school. It's actually true. You know, who doesn't know commutativity? Who doesn't know associativity? Who doesn't know the right cancellation law? Do you know what I mean? Like
Yes.
every child knows this.
Mhm.
You know, why do we need to prove such an obvious fact? Well, we do not at all. We can accept it without proof, and that's what they do in school. And why do we prove it? Well, for fun. It's just like solving a crossword or completing a picture puzzle. Some people find fun and pleasure in deducing new facts from some quite similar, dissimilar facts. I do not see any fun in it. That's what the other person's saying. It's like a conversation.
Yes.
I mean, and I mean, I really appreciate this. And if you don't, then maybe you shouldn't be in the class. You know what I mean? Honestly,
Yeah.
objectively speaking. But if you do appreciate this and say, whoa, something's actually not right with the way things are done,
Mhm.
well, then it's good, to make sure that you
Yeah.
can correct what isn't quote unquote as proper as it should be. Um, yeah, yeah, and besides this, reveals the very method of mathematics, its core and
Yes.
spirit, which is it's just pure logic, right? Um, we're not like you're just saying things. You repeat after me. We're actually proving some stuff. So
Mhm.
exercise 1.5, we have 1, 2, and 3. Let's talk about these really quick. I don't want to do them, but
I have a
maybe we
question.
will. Yeah, please.
Are there any other types of math or number systems that are derived from different types of axioms?
Well, that's a funny thing. I mean, yeah. Okay, to get our real number system, you're going to need essentially field axioms. You're going to need 10 field axioms, right, to get our real number system. And, that's generally accepted. And without all of them, you're going to get multiple number systems that will work. I'm talking about the real numbers right now. Just so you know, the way this book was introduced was natural numbers, not real numbers.
Mhm.
So I'm answering, I think, a more proper question. Okay, so I'm rephrasing your question and I'm answering in that context. Is that okay, Mr. Rumi?
Yeah, yeah.
So as far as our real number system, it's derived from the field axioms, right? And so if you don't use all of them, you're going to have multiple number systems that are going to satisfy this incomplete thingamajig, right? And once you have that, then what you have is the beauty and the magic of the real number system. And when you learn this stuff, you don't know the beauty or the magic. You're just given it, right? You don't know where it comes from. You don't even know what these axioms are that develop the real number system. So I think that's a little strange, right? I think that's definitely kind of,
Yeah.
you know, just weird, right? Just
Mhm.
weird, quote unquote strange.
Yeah, which is there's this. I really like the analogy where they were talking about the a difference between physics and math, where they were saying in systems for math, you can say something is some way, and then that very act of saying it makes it that way, rather than some kind of thing in physics where you have to observe the different things in the world
Yeah,
and try.
Avi, I'm gonna respectfully kind of disagree with you a bit on that. Like what you're talking about is, when you know what you need in math, you can define,
Mhm.
either a structure or you can define something a certain way and make it so. And then if it works, then you have like a publishable result. And I would agree with that statement that usually when you define things well, you get like literally publishable results. So the whole job of doing all your work, in many cases, many papers I've seen are based on people defining things properly,
Yes.
and I would agree with that. However, that's just like, I mean, the classification that you just made, I would respectfully disagree with. I would
Uh,
say math is looking, is just pure logic, pure truth,
yes.
and physics is applied math, right?
Yes. Exactly.
And so it's not quite as let's just say it's not quite as sophisticated. Let's say in that
Yes.
context. Just for clarity, I told Rumi this, but I studied for a semester in the physics department when I was a graduate student. And, I was a decent student in the math department, somewhat talented, somewhat lazy. And I went over to physics and I became like some kind of genius and stuff. It freaked me out tremendously.
Hmm.
Yeah, I just spent a little while over there. I had to get out of there because everybody was like razzing me. They're like, "Oh my God, you're so good." I'm like, "Oh, man." Yeah, so I would say most of the physics, faculty and students, from my observations at a serious research university, didn't have as much math background as they needed to
Yeah.
do what they needed to do.
Hmm.
And I studied with Dr. Burkhardt, who was a phenomenal mathematician. He was a physicist, though. He was not like a mathematician by trade. He was a physicist, but he was phenomenal. Yeah, I spent a
Yeah.
lot of time with him.
And basically, that's true for any area of science. You want to have a really firm mathematical background so that you can have that as a base for all of
Well, I would argue that, yeah, first of all, physics is applied math, engineering is applied physics. So engineering gets really easy when you know the math.
it. Hmm.
Um, you know, Economics, they have mathematical economics, and
Yeah.
you can get results like hotcakes when you have the math. I studied in the economics department in graduate school too, indirectly. I mean, that wasn't
Yes.
but I did a lot of work in economics, and it's very straightforward. And I was full-time faculty computer science. And when I studied computer science, they all thought I was really good too. It was really weird. It's just anybody who leaves math goes into another field is instantly anointed like some kind of weird genius, which, better or worse, it is what it is.
Interesting.
No big deal. Okay.
Hmm.
So, all right, all right. Let's talk about this. How in the world are we going to play around with, if y'all want to pick one, how are we going to play around with, you know, one, two, or three? How about two? Let's play around with two. Let's talk about getting a solution. I don't want to solve it for y'all. I want
Well,
y'all to play
if
around.
if you have the same variables on either side of the equal sign, couldn't you just using commutativity and uh, 1.2.5 commutativity and associativity, couldn't you just rearrange it until it's the same? Or by proving that those are equal, haven't wouldn't that already be evident from those from commutativity?
Yeah. So first of all, I completely agree with you. But looking specifically at two, I
Oh, I
don't
think I
think.
know.
Yeah, go ahead. Yeah, go ahead. Yeah.
Yeah, so let's see. Move. Okay, so there's three terms, right? In parentheses, a plus b, and then we have c, and then we have d, right? And then, well, actually, technically, if you look at it from the big picture, it puts it as two terms, but there's like we can act as if there's three, right? And then in the big parentheses from associativity, we put the parentheses around b and c instead. And then now we have three terms A, D, and we have B plus C as a term. And then we can do associate. It's basically just a bunch of associativities, right?
Don't
Yeah,
commutativity because actually, yeah, commutativity would
yeah,
interchange these. Yeah, you
yeah,
have to be very careful with the associative steps in
yeah.
number two. But agreed, like that essentially it is, a game of associativity to go from
Right.
one to go
Hmm.
to the next. And yeah, no, it's good. So, and to make it clear, from number, starting from number two, the problem I see is A plus B is the problem, right?
Mm.
Because C is an element, D is an element. A plus B is nasty, right? You can substitute X as A plus B and just, it should flow a little bit better, right? It should flow a little bit better for a little bit. And then obviously you're going to have to substitute back the A plus B. And, no big deal. I think Rumi, you didn't even do a substitution. You just did it, which is awesome as well. But, you know, to each his own. No big deal. To each his own. Um, Anybody want to take a stab at number three? So how about you all try one, two, and three? Does anybody want to take a stab at number three?
Hmm. So you got A is less than B, C is less than D, and then prove that A plus C is less than B plus D. Huh.
How are we going to do that?
So you're gonna need commutativity for that.
No.
Oh, no, it's all associated.
How's commutativity going to give you anything on that one?
Yeah, exactly. Because there isn't.
No. Any ideas? I'll give you a hint, but I'm not going to do it. So this is not going to be done today.
Well, you could do then if A is less than B, then A is less than B plus 1, and
Yeah, I don't want to
C
go
is less
there.
than D plus
Yeah,
1.
I don't want to go into that. I agree with you, but let's not go into that.
Hmm.
Rumi,
Can we say that A plus C is less than B plus C, right? We know that. And then we know B plus C is less than B plus D, no? Because C is less than D?
oh, that's an interesting little trick. Yeah.
Maybe. I don't know.
Yeah,
I
that's
vaguely recall doing this before. I think maybe in my proofs class. I don't remember.
Yeah,
I think I did this before.
Maybe we'll get away with that. I did it a different way because what you're doing is okay. What I use in my head is 1.5.6. You have a Z1, A plus Z1 equals B. B plus Z2 equals D,
Oh.
right? And
Ah.
so A plus C plus Z1 plus Z2 equals the B plus, right?
That's kind of confusing. I think it would help if it were actually drawn out, but
Yeah.
I'm not
If
gonna
we
draw it
wrote,
out.
if we,
I'm not going to draw it out because this is an exercise for you to figure out. Yeah, next time I'll do it, but not today. I'm just giving hints. So, no, I like Rumi's technique. If that, you know,
'cause
plays,
you couldn't just join it like A is less than B and just add a plus C so that B plus C would be less than D in the middle. That wouldn't work. Because they're two separate statements, really. I mean, to join them, you would need a common variable, I would think.
yeah, but you can actually put an equality using
Yeah.
1.6 and try to use 1.5.6 to logically deduce. You know?
But, that's interesting. Okay. Because you don't know that A is less than or equal to B. You just know that A is less than B.
Yeah, no, I like Rumi. It works. Just so you know, I like Rumi's approach a lot better than what I do. I
What
think
again?
it works perfectly. 1.5.6 works perfectly. Rumi's is better. Yeah, it works. Rumi, do you see what you? I don't want to do it because I need y'all to try it out. Do you see it, Rumi, or no?
I think so, at least. I think I see it. I mean,
It works.
I might be
You
wrong.
said you can apply 1.5.6 to that because 1.5.6 was dealing with. Oh, I see. Because it's saying x is less than y in 1.5.6. So you do have two variables in an inequality.
You say A
So I
plus
guess-
B1 equals B. Is that okay?
How could you say that? Oh, you're saying that. That's your assumption is that like, we're saying that A plus B1.
1.5.6.
Yes. And then
Then C plus Z2.
equals B, and then proving that Z1 and Z.
And I'm not going to say any more, right? I actually like Rumi's proof better. I honestly think this is the right way to do it in this class because we're using 1.5.6. Rumi, you did a little cute little trickster stuff, which didn't use any of the material that was covered. All right, just one second. No, it's legit. Rumi's is very legit. I mean,
I-
the material that we covered essentially, to be completely honest with you.
Okay.
But it didn't use
Kind
1.5.
of confused, but okay.
Yeah, I like Rumi's argument.
Okay.
ahead.
Well, I'd like to see it written down at some point, but
Yeah, next time, not
yeah. Okay.
not today. I'd like to write it down next time. Rumi, you can have a turn next time if you want. So you all try 1, 2, and 3. I'd like to write up 3. Just for kicks.
So that's what we'll do next time.
Oh no, that'll be quick though. That'll take.
Yeah, that'll be part of what we do next.
Yeah, next
So,
time, Rumi, I need some more scans. All right.
Yeah, I'll give you